Cool. I think we're getting a few more trickling in, which is great. I think in the interest of time, though, as we let these good people come in, I think we kick off because I know we've got quite a lot of content to cover. Yeah, so hi everyone that's here so far. Hopefully we'll get a few more people coming in. For those of you who don't know me, I am Alex Oliver. I'm the Partnerships Lead for the REWIRE Innovation Knowledge Centre. So just a couple of bits of housekeeping before I introduce the presenters for today. So if you do have any questions, feel free to add those into the Q&A or the chat. I will be sort of relaying those onto the presenters later on. And I'll be sharing a few links as we go through as well to other bits that might be of interest to you. But yeah, I'm delighted to be joined by both Paul, Meredith, and Saeed Jadhi. So I'll just introduce those quickly before we get them presenting. So our first speaker is Professor Paul Meredith from the Swansea University. He is Professor of Material Science and Sir Cymru National Research Chair, and also holds an honorary professorship at the University of Queensland in Brisbane. Paul's research interests span sustainable advanced materials for applications such as solar energy, optoelectronics, bioelectronics, advanced concepts in semiconductor heterogeneous integration, and decarbonization of semiconductor manufacturing. And Paul is the director of the Centre for Integrative Semiconductor Materials at Swansea, which we'll talk about today, which is a research centre and innovation facility at the university, which brings together semiconductors. Oh, I've lost my screen there. Semiconductors and advanced materials platforms to research and develop new technologies and products. Our second speaker will be Dr. Saeed Jadhi, who's an assistant professor of power electronics within the Electrical Energy Management Group at the University of Bristol, and is also part of the REWIRE academic team. So Saeed received his PhD degree in power electronics from the University of Warwick, and has worked in industry at General Electric Grid Solutions as a power electronics engineer and line coordinator for multiple European projects. His research interests include wide bandgap power semiconductor devices in power electronics, and we'll be talking about why these technologies are so important for society meeting net zero. So without further ado, I will hand over to Paul to present his slides. Saeed, for him to crack on. Yeah, so I can see your slide, Saeed.
Super. Let me just see how can I get this pointer right. So thank you everyone for attending today. Paul very well and comprehensively discussed the fabrication activities that are going on, especially in the South Wales. I would like now to discuss a little bit more on the reliability and the packaging activities that are happening at Bristol, and basically the collaboration that we are having. So today, global population 8 billion. It just gets increasing. We will need more energy. You can see the impact on the weather right now in July in the UK. It's unorthodox. It's getting very hot, so we need to address that. And the need for energy means that more global warming, more basically heat generated, more power losses, unless we actually actively act upon it. So how to address that? There are solutions, for example, integrated at the beginning that IEEE has been proposing for a long time now, trying to connect distributed energy resources to the grid, and also even concepts such as DC distribution, or trying to make converters and power electronics embedded right at the very stage of the power grid to improve the power losses, to enhance the reliability, and making sure that we can have more, we can achieve the net zero faster. And another aspect of that is obviously the electric vehicles. Tesla has been at the forefront. There are a lot of other companies that are fabricating EVs too. And some of them, like this Tesla Model 3, has been utilizing silicon carbide power devices. Some of them are still at silicon, but there is a large landscape of different technologies and different devices that are being used to deliver these EVs, both at the drivetrain stage and also at the chargers. So if you want to deliver that, there are, in addition to the semiconductor devices itself and in addition to the actual fabrication of the devices, as Paul was mentioning, we also need to take care of the integration, which means the packaging and also the long-lasting reliability and the performance of the modules and the devices to make sure that they are able to cope with a 40 years lifespan that you would expect from an EV charger. So why just not continue using silicon power devices? Simply because the electric field level is limited. As you increase the voltage, this triangle here will become larger and larger. The device will become very thick. The peak electric field will eventually reach the critical electric field. You want to expand the voltage further. The device will become even thicker. The doping will go down. And effectively, you cannot fabricate very high voltage devices with silicon that are efficient enough for very high power grid level applications. So there is a limit. We need to address that. Now, in terms of the reliability as well, we need to be very careful. There are very severe consequences for failures, but there are degradation indicators. Some of them are independent, some of them are interdependent. So you can, by monitoring and condition monitoring of the performance of the devices and observing some of these key parameters, you will be able to tell whether the device is actually degrading toward failure and whether there is something you can do to prevent that. And we call that, for example, in EVs, we call that limp home mode, which is effectively if you detected that your devices are going to a degradation, you can reduce the power consumption, electrothermal stress will be reduced, and you just deliver to reach home, and then basically will take a maintenance and closer observation of what's happening with your devices at the heart of your drivetrain. So if you want to look at the reliability, there are so many papers you can read. I will just mention some of them that are prior 2017. For example, this one is saying basic mechanisms of threshold voltage instability and implications for reliability of silicon carbide MOSFETs. There are others too, gate oxide reliability on the short circuit, single event defects, single pulse avalanche mode for silicon carbide MOSFETs, general reliability issues. But what is important is that all of these papers are just talking about silicon carbide MOSFET generically, because most of them were published at 2017. And at the time, all silicon carbide MOSFETs were planar. So you need to be careful when you are reading these papers, because with trench devices that have been commercialized more recently, about the past 5 years or so. So this is what ROHM introduced, the double trench silicon carbide MOSFET. Infineon started with asymmetric single trench ones, and these basically change a lot of those understanding that we have had in terms of reliability of planar silicon carbide MOSFETs. So there are super junction MOSFETs that are mainly made at silicon at this stage. There are some prototypes in silicon carbide too. There is silicon carbide planar ones. There is symmetrical double trench from ROHM, and there are asymmetrical trench MOSFETs. Again, this from Infineon. And each of these companies, they have developed their own patents, their own benchmarks in terms of performance, but the reliability of the devices also changes a lot with those changes. Also, the die structures are becoming smaller and smaller. The cell pitching in making the devices will become more aggressive, and that is to increase the yield, to reduce the cost, but then that again will have implications on the reliability. So in terms of the EV chargers or EV drivetrains, one of the key parameters is, for example, short circuit. So we have done measurements on that. We have developed the TCAD models for it, and we can see, for example, that planar devices are performing significantly better than the existing trench symmetrical or asymmetrical trench devices when it comes to the short circuit reliability. This is obviously the state of the art of the devices for the past few years, but things are improving. So hopefully trench structure will also be able to catch the planar ones in that sense too. The same is applying in terms of avalanche. In terms of avalanche, trench and both symmetric and asymmetric are not too bad compared to the planar devices, but there is still bottlenecks that need to be addressed. So if you want to have heavy-duty power modules for heavy-duty chargers, for example, trucks or buses, if you want to electrify these, there are multiple stages of conversion. You need to connect basically all these power modules to the distribution level. You cannot have enough power from a very low voltage 400 volts grid for heavy-duty EVs, and that means that you will have a first stage of active rectification that can happen with silicon carbide MOSFETs. Then you will have a second stage inversion again back to AC, but you can increase the frequency to 1 kilohertz, and then you will have an active rectification again, which will be connected to 800 volts DC buses, and there's even 1000 volt DC bus that will be connected to the battery. And to enable this, there are multiple power modules that are produced by manufacturing in commercially and also in research environments around the world. But the bottom line is that most of these are still low current, and we will need to increase the power rating of these devices, of these modules, to be able to cope with that level of demand. To address this revolution, there are two also other basic ancillaries that we need to address. One is the solid-state transformers that will reduce the size of these transformers to enable them to become more ubiquitous, installed across the distribution level. And the other one is modularity, because you want to have power electronics building blocks so that if there are failures, you can quickly change and maintain the power modules, the building blocks, and continue operation, and all the maintenance should happen offline elsewhere. To enable those power electronics building blocks, at Bristol, we have two major technologies that will help with that. And this is the work of my colleague, Professor Stock at the EMG Research Group. The first one is advanced sensing. So we have infinity current sensors that can detect both the source current, drain current, and also the gate current. And they are able to have a very high bandwidth, enable you to detect exactly what's going on inside the gate of the device. And the second one is advanced gate driving. So we have developed active gate driver chips that would enable to drive the device very fast, and we can have arbitrage, basically waveforms here that will be in step functions and enable you to detect and change the gate current as and when necessary. So that enables you to have a very fast switching with minimized oscillation, minimized overshoot, which will in turn enhance the reliability. In terms of the packaging, there are some proposals around the world. For example, in this module, this is the two-level, basically ceramic and three-layer copper sandwiched. This is for a 10 kilovolt module that is basically shown here. And this concept enables you, if you connect the middle layer to the middle point of the DC link, it enables you to reduce the partial discharge, as you can see here. And that in long term will increase the reliability of your system. So we have tried to fabricate some power modules. We have a project at Bristol that we are working on packaging too. But we are not working at 10 kilovolts. We are working at 1.2 kilovolt ordinary power MOSFET modules that are used for example, drivetrain of EVs. So this concept directly will not be useful for us, because if you go to 1 kilovolt instead of 10 kilovolt, that partial discharge is not significant. So there is no need really to go to double layer basically ceramic to address that. However, doing that even for 1.2 kilovolt, if you do it in a smart way, can still give you some advantages. So this is about an EPSRC project that we have. We are working with multiple companies: Amantis, Compound Semiconductor Application Catapult, Fraunhofer Microchip, Wolfspeed Dynex, Corvo, TPS-GE, and Omicron, in an effort to make the power modules to minimize the parasitic inductance, minimize partial discharge, and at the same time, if possible, try to embed the sensors and the gate driver chips that I just showed you within the module to improve the performance and go outside the box in terms of the performance of the silicon carbide modules. So this is starting with this very basic concept. This is single layer DBC wire bonded, typical structure that you would expect for most power modules that you can see, and we have got our sensors already embedded on it. But we are also looking at the to change the bus bars here in the terminals in such a way that will minimize the parasitic inductance, and we are using polypropylene plastic sheets in between to ensure the isolation too. And if we connect the this is a double layer ceramic, instead of connecting the middle point to the middle point of the DC link, we are using the middle layer as a return path for the current, which in turn will increase the mutual inductance, and the overall parasitic inductance of the module can be reduced with this concept, even for 1.2 kilovolt. We are also developing some wire bondless modules, both in vertical and planar busbar structures, to try to minimize the parasitics, because that is the main bottleneck in packaging of devices. And we also have concepts that we don't have no base plate is required, even if we use this double layer substrate here. So this entire base plate can be removed as well. And as you can see here in this picture from a side view, there are 2 layers of ceramic, 3 layers of copper, and current is going back through this path, and that effectively, that mutual inductance will cancel a significant amount of the parasitic inductance that you may have. So we are still at this, basically, we have finished the design stage. We are working with Catapult and CSA Catapult and a lot of these other companies trying to fabricate these modules now. Hopefully we'll have some actual prototypes within the next few months or so. And we are also trying to both having the wire bondless modules, which will be effectively current conduction will happen through the wires on the PCB, and also wire bonded modules that are more standard modules that you would expect to see. We have done the COMSOL modeling too. Well, by we, I mean our PhD students and postdocs, and we can see that the temperature rise in terms of the devices and the maximum temperature that the modules have to endure is acceptable. The partial discharge and the max electric field is within the limits that you would expect, and this double layer ceramic can also actually alleviate that as well. And finally, we also do a little bit of work on gallium oxide too, as Paul was mentioning. They are doing the fabrication. We have a team in Bristol, Professor Martin Kubal, Dr. Matthew Smith, and the team also fabricating the gallium oxide devices. There are multiple basically structures that you can make the devices, and basically the bottom line is that we are trying to go to the beta gallium oxide limit to improve even the performance beyond what silicon carbide, the gallium nitride, can achieve. They have already fabricated some earlier stage chips. They're 1 centimeter and 1 centimeter, effectively 9 devices within the same die. These are rated at 4 kilovolt, and each of the basic devices can handle about 5 amp or so. So it is effectively coming together, and we have done some earlier stage simulation analysis. We have considered some theoretical, hypothetical HVDC or MVDC cases, and we have looked to see if whether gallium oxide actually can have an opportunity in future for basically power electronics applications. So this is our methodology. We have considered the HVDC, VSC, HVDC converters, and we have gone through the normal power losses, for example, calculations, etc., that you would expect. And we have seen that the earlier stage gallium oxide, in terms of, for example, the case temperature or the converter power losses, has been really bad. Compared to silicon IGBT and silicon carbide MOSFET, gallium oxide was not performing, and the power losses was too much. The case temperature was too high for reliability. But there is hope. There are a lot of concepts. For example, if you make the devices on diamond and then go to super junction structures, etc., you are able, at least theoretically, to catch the performance of silicon and silicon carbide in power electronics too. And the main enabler here is that the devices will become very high voltage, so you can effectively replace 5 to 10 devices of silicon or silicon carbide with a single gallium oxide. Obviously, there is a lot of problem in terms of current handling capability and also the thermal, but we are hoping that this fabrication on diamond can help alleviate part of that. So whether that is actually true or not, we need to demonstrate. So we are trying to, as I said, Professor Kubalsin, they have already fabricated the gallium oxide dies. we are trying to package them. This was the first concept, but this is for discrete devices, very low power. So instead we decided to go to a power module packaging, something similar to this. And we are currently working with a CIL custom interconnect company that we are collaborating on, jointly trying to package and demonstrate this module. And hopefully once we have actually done that, we will go to the next stage of actually building a converter and then assessing the efficiency. The first stage, we don't have high hopes, but obviously this is research, so hopefully eventually it will improve. And that's about it for me. Sorry I spoke too fast, but I just tried to catch up with the time. I appreciate that some people may need to go.
Great, thank you very much, Saeed, for that. And yeah, very, very speedy, and you managed to get through a lot of content there. So yeah, I'm thankful for you doing that in such quick time. Great. So if anybody has any anyone has any questions, feel free to add them into the chat or the Q&A. We have already had one through about, so this poll is specifically for you. So nice to see plans to reduce SF6 being emitted into the atmosphere. Could you expand on those plans and what you're planning on sort of doing within the sort of the SynZero project for that?
Okay, thanks. That's from Matt Smith. So there's two aspects to this, right, Matt? It's could we envisage different chemistries, and potentially with the same chemistry, more efficient process. That's the first thing. I don't particularly believe at the moment that a lot of progress has been made on that replacement strategy. Although I know, I mean, for example, there are active attempts to particularly replace SF6 with other fluorinated and fluorinated combos, which have maybe got a lower greenhouse gas warming potential. But the thing that we're working on within SynZero at the moment is more efficient sort of handling of the gas itself, the waste gases themselves. So at the moment, when you want to burn an F gas, when you want to get rid of an F gas, what you do is you combust it with methane and oxygen in what's called a burn process, and that reduces the SF6 essentially to hydrofluoric acid. In that burn process. Now, it's I mean, it's obviously not very nice burning methane and oxygen to get rid of your SF6, but it's certainly better than just squeezing 24,000 times CO2 out of your scrubber. So at the moment, we've got an experiment planned where we're looking at replacement of that burn washer process, which actually it reduces the emissions intensity by several thousand times to about a couple of hundred. But with Edwards, we're looking at what's called a plasma burner, and that's a direct reduction of the SF6 or the fluorinated gases using a hydrogen nitrogen plasma. So essentially what you're doing is you're using electrical energy then rather than methane and oxygen burn energy to directly reduce the SF6 to HF. Once you have the HF, you can then salt it, neutralize it, and it can go off to watercourse as calcium fluoride or sodium fluoride. So that's the current sort of best practice. Do these plasma burners work? We don't know. We've got the first prototype from Edwards, and we're planning an experiment as soon as we've got the funds to do it, because it's quite an expensive experiment to do, where we'll put a standard so a standard burn washer, methane oxygen burn washer, in parallel with the plasma burner, run, for example, a standard ICP-H with SF6, monitor the inputs, monitor the outputs with FTIR, and then look at the relative efficiencies of the reduction process. So that's a very specific experiment that we'd like to do. And we have the equipment, we just don't have the bandwidth and the resource to actually run that experiment at the moment. So if anybody wants to give us some money from REWIRE, we'd love to do it.
Always looking at new collaborations, Paul. So we can always look at that potentially. So yeah, happy to follow up on that. I haven't seen any more come into the chat, but I've just got a very broad, generic question about if we're thinking about the sort of net zero and sustainability space, do you see like one or two particular areas where semiconductors and power semiconductors specifically can have the greatest impact over the sort of next 5-10 years?
I personally would say, firstly, that I'm very interested to understand the carbon emission from the very fabrication of these devices, because you are trying to fabricate devices that will address the global warming, but you don't want to create additional harming in such a way that you cannot offset with it. So that's the main thing. But also, obviously, electric vehicles are becoming the mainstream. And by the way the policies of all governments around the world are going, I suppose that is the main basically area that this can have an impact.
I think I'm going to channel my inner Mike Jennings now, but Mike is always at pains to demonstrate the problem with multiple converter stages in a renewable to grid system, and the conversion losses as they add up. For example, when you bring offshore wind into an onshore grid, and there, if you have a 10 or 15%, maybe a 10% loss per inversion or conversion stage, then that gradually builds up, and you end up losing 40 or 50% of your clean power in some circumstances. So that's one area where even relatively small efficiency gains, with more efficient power converters, could have a very big impact on the overall power system and energy system.
Great. We've had a couple quick ones come in, so if you've got a minute or two left, then we can go into those. So Ahmed's asked, so talking about gallium oxide specifically, how does the ease of fabrication of gallium oxide compare to that of silicon carbide, and could gallium oxide offer a more promising path in terms of manufacturing?
I think that's for Paul, really, but because I don't do manufacturing, but as I said, my colleagues in Bristol are doing, and also Sims in Swansea, they do a lot too. So maybe Paul can shed light more on that.
Yeah, look, I went to the ultra wide oxide meeting in Strathclyde a couple of weeks ago, which was really interesting, and there are some really basic, very significant challenges. One is p-doping. Because of the relatively flat density of states there, what happens when you try and p-dope it apparently is that the donor gets very strongly coupled to a polaron, and ceases it loses its donor character. So p-type doping, I don't know, could be impossible. I'm not so sure. I'm not so sure about that. There have been claims. So that's one thing. And if you can only make unipolar devices or heterostructure devices, as we're seeing in Saeed's talk with those devices, nickel oxide, for example, then that has limitations. I'm a solid state physicist, so I think about structure and density of states every day, right? And from what I've seen, the sticking point is probably going to be the availability of high quality gallium oxide wafers, so that we can grow homo epitaxy, whether it be a beta phase or some other phase, so that you can begin to grow thick epi structures and sustain these high voltages with low defect densities. I know there's some progress being made on rationalizing high quality gallium oxide wafers for homo epitaxy, but I think that's another big manufacturing problem as well, because if you can't, I mean, so for example, the 0001 C-axis sapphire epi has a 6% lattice mismatch. Silicon carbide, it's about a 1% lattice mismatch, I believe. Those are not acceptable for high quality, low defect, reliable power devices in particular. And so I think I was discussing this with colleagues up in Strathclyde and various other places, but I think at the moment what I can see is that the power space is going to be limited by these factors of only unipolarity, no p-doping, and the quality of the epi. So I think the first types of devices we might see outside of this audience is probably deep UV optoelectronics, where the requirements for the quality of the material and the defect densities are probably less. So that's where there's a lot of activity going in. So there's some things to overcome: defect density, homo epi, p-doping.
Great, thanks for that. I know we've already run over by a few minutes, so I think we'll cut the questions there, but yeah, I just want to say a massive thank you to both Paul and Saeed for those really interesting talks, and also thank you to everyone for attending today. Yeah, I've put a link in for our next webinar, which is in about a month's time, which is on a very different topic on scanning probe microscopy, but for wide bandgap semiconductors. So yeah, feel free to register for that. But yeah, thank you very much, everyone, and hopefully you get to go out and enjoy the sunshine fairly soon.